Hello and welcome to today's video. Today's video is going to be a bit of a short one, but it's an introduction. To start out, I wanted to re-highlight two big ideas that we're going to go into this chapter, and one of which you may recall from my introduction to calculus. And these problems are going to be the tangent and the velocity problem. So get started with the tangent problem. Suppose that we have a graph. Alright. And we are just going to call this graph f of x. Now, suppose that we have a point on this graph, x, which would have a coordinate f of x, or x f of x. Well, we know how to find the secant line. It is really just x2 or f of x2 minus f of x all over x2 minus x. But what I wanted to suppose is, what if we call this point x of x, or sorry, x plus h, f of x plus h. F of x plus h. Well, as of right now, if I were to take and draw on the secant line here, what you'll notice is it's almost zero. But what happens if we bring this point closer? Let's suppose that we are now bringing the slope, the secant line, closer to x. Well, our new tangent line is now negative, interestingly enough. But if we bring it even closer, it's now positive. And what calculus really supposes is, what if we bring these infinitesimally close to each other? And that is the idea behind the tangent line. It is that as these as x of, or x plus h approaches x, we will get a better and better approximation for the tangent line, where eventually we will get the tangent line itself. So this is highly dependent on the difference quotient. So it's important for us to know how to use it. So I've got a few problems here. If you want to work through them yourselves, you can. I'll give you a moment to do so. And I think that's enough time, especially if you pause the video. To start out with this, I have given us an x coordinate to use and an h to use. So we're going to start out by plugging in this value for x, and we'll plug in this value for h later. So we have f of x, which in this case is going to be 2 plus h, as is our different quotient, minus f of x, which is 2, all over h. Well, let's see. So this is really just the same thing as 1 over h times by, well, we can plug in the 2 plus h for x. So this is going to be 2 plus h plus 3 minus 1 over 5. Now let's see, what can we do with this? Well, there's a lot we can do. We're going to cross multiply. So we can get common denominators here. So I want, and I'm just going to rewrite this real quickly as 5 plus h. So we are going to get 5 over 5 times by 5 plus h minus 5 plus h over 5 times 5 plus h Well, this is the same fraction, so what I'm going to do is I'm just going to draw in the bar and subtract. This is technically now a negative h. These 5's are going to cancel, leaving us a negative h over 5 plus h. Alright, and we know that this is still times 1 over h. The h's will cancel, so we now have negative 1 over 25 plus h. Alright, gotta delete some stuff. Make some space. And I'm going to move this over here as our answer. Wait, I did forget one last thing. And I did say approximate it when h is 0.01. So, we do negative 1 over 25.01. And for our slope of our secant line, with that approximation for h, we will get negative 1 divided by 25.01. We will get approximately 0.039. And that, my friends, is our answer for the first question. Alright, now let's delete that. Now let's do the second problem. So, once again, we are going to plug in 2 for our x value. So we are going to have f of x plus h, which is just 2, minus f of 2 all over h. Well, we will have, put in 2 plus h for x. So we have 4, because 2 plus 2 is 4 plus h, minus the square root of 4 all over h. What can we do with this? Well, let's multiply by the conjugate. That way we can maybe get rid of these radicals. So the conjugate is going to be just the opposite sign, so it's going to be plus instead of minus the square root of 4. And we have to keep the equation constant, so we also divide by the conjugate. Plus square root of 4. And what we'll see is if everything's done right, this and this will cancel, creating a 4 plus h minus a 4 all over h times by the square root of 4 plus h plus the square root of 4. The 4's here are going to cancel. These h's are going to cancel, leaving a 1. So all we are really left with here is a 1 over the square root of 4 plus h plus square root of 4. Alright, I'm going to delete some of my past work here, make it a bit easier to move forward. Alright, and now we're just working with this. Well, h we said is 0.01. So we have 1 over the square root of 4.01 plus the square root of 4, which is just 2. Punch that into our calculator. Give me one moment. And as you can see, I got my calculator pulled up. I got this program. It's kind of like a TI-84, which makes that useful because that's like one of the most common calculators that is used. So we are going to do 1. Let's see. I don't know if this one has. I'll have to look into that later. So we are going to do divided by, in parentheses, the square root of 4.01, all right, plus 2, and we get an answer of approximately 0.249. That, my friends, is the answer for that problem. All right, give me one more. Continuing on now, we're going to now address the velocity problem. And this velocity problem is, well, let me first suppose, what is velocity? Well, velocity is technically defined as change in position x over time. So, in most cases, we can get some sort of average velocity using that. However, let me, whenever you're driving down a road, your speedometer on your car is almost always changing. And that's because there's forces acting upon it. But that just means that we can't use a linear model, or most models that we have right now, to truly approximate the distance your car is going or its speed at any given time. And that's the velocity problem, the entire idea behind it. Or whenever you push a ball on a desk, eventually it's going to come to a stop. Its velocity is constantly changing. So I've developed a problem here, and this is just asking for average velocity, as we don't have the tools yet for this instantaneous velocity. So let's start out by finding the average velocity from 1 to 2. Well, V average is going to be the same thing as S of t. S of t is a common way of saying position, or t2 minus S of t1 all over t2 minus t1. And this is incredibly similar to our difference quotient. I'll explain why that is here in a moment. So, I'm actually going to move this because this is going to be in the way. There we go. So, let's do this first one. VAV is going to be equal to S of 2 is 250 minus S of 1, which is 100, all over 1. That is just 150. And I don't have any units listed, but let's say this is feet per second. So this would be 150 feet per second. II is going to have a V average of, well, S of 2. So that would be, S of 3, which is 450, minus S of 2, which is 250, all over 1. So once again, that is going to be 200 feet per second. And if you don't know where I'm getting this denominator from, I'm taking the end time, which is 3, minus the beginning time. Let's do III now. VAV is going to be equal to, well, in the denominator, 3 minus 2, that's just 2. And in the numerator, 450 minus 100. Well, that is just equal to 350 over 2, which is 100, or I believe that would be 175 feet per second. Alright, I'm going to clear the board here. And now let's do IV. So, the velocity at 6 is 100. The velocity at 3 is 450. And the time difference is 6 minus 3. So we have negative 350 over 3. That's not going to work out nicely. Sometimes that happens. Well, to approximate that, we will have negative 350 divided by 3, if I remember correctly, and do my head math right. That would be negative 116.7 feet per second. And finally, let's find the final V average for number 5 there. So we will have the time at 5, which is 250, minus the time at 2, which is 250. Oh, this one's going to be easy. 5 minus 2. Well, the numerator is going to turn out to be 0, and the denominator is going to come out to 3. That looks like that's going to be 0 feet per second. So obviously, they did not move at all during that time, but that does not mean that exactly. And you'll see at different points there can be different velocities. Well, that's all I have for you. Just to make one final note here, the velocity problem and the tangent problem are incredibly similar, as you'll see going forward in this chapter. But I hope you all have a wonderful rest of your day and enjoyed. Goodbye.